you say any permutation.
Okay.
I have that. So I product.
Get started. Should we start?
Yeah. So I think everyone is back. If not, they're going to be late and it's going to be fine. Right?
Yeah.
Well, yesterday I opened up without a speaker in the room, so I think that's so the second part of this morning will be Jeremias, who's going to be talking about optimization point of view on variational inference connections with Bayesian inference, I want to say. Yeah, floor is yours.
Yeah. All right. Well, thanks, Francesca. So I have the pleasure of bridging you over to lunch. So I'm trying not to go too much over time. I'll judge by how many people are on their laptops and their phones, whether I'll end early. So if you want me to end early, look really uninterested. So what I'm going to speak about will be they'll be connected to variational inference, because that is where my motivation and my drive came from initially, but it also has diverged from it. So it'll be like an exploration of a bizarre landscape, I suppose. The problems that I'm studying very, very loosely, I call them optimization-centric generalizations of Bayesian inference. And the reason for this is that I'm coming at Bayesian inference from a variational perspective. And I'm trying to take that perspective and see what we can do with it once we start playing with it. The way I'm structuring this today, here we go. So the way I'm going to structure this today is essentially with this one graphic. So if you've been unfortunate enough to have attended one of my talks before, you likely will have seen this before, because I usually start and end with this. The bit in between will change, though. It's usually different from talk to talk. But this is basically the message that I've been trying to refine over the last couple of years. And that is that whenever you do Bayesian inference, you're already solving an optimization problem anyways. And this optimization problem has a couple of assumptions associated with it, some of which you may not really want to have to make when you apply Bayesian inference. And in particular, this is the case in machine learning, which is where I've dabbled quite a bit. And if that's the case, you may choose to pick a different optimization problem in the space of possible problems to solve and run with that instead. And in many cases, I will argue that is actually a more interesting problem to look at. Okay, so the way I'm going to structure this is in 3 blocks. So first, I'll make a couple of outrageous claims and make all of you angry. Then I'll try to justify some of them a bit with theory. And then in the third part, I will hopefully convince you that even if what I've claimed is outrageous, maybe the outcomes of it are perhaps useful. Okay, so let's start with why we do variational inference, why we do MCMC, why we do Bayesian computing, and that's really Bayesian inference and Bayes rule in particular. And when we do Bayesian inference, really, what we conceptualize is that we want to know about a true state of the world, some state S. We have a prior belief about that state S. We get some new data, and then we update our belief about the actual state of the world by combining our prior beliefs with the data. And that way we get uncertainty quantification, right? That's not going to be news for anyone in this room, but I think it's important to remind ourselves why we do Bayesian computation in the first place. And when you conceptualize this in a graphic, this is one way of doing this. So you start out with the state of the world that generated the data that you have also got to formulate a prior belief about at some point. You also have to pump the true state of the world through some kind of model, right? So in order to make any statements about your prior beliefs of the world, you need to pose a model. So that means all your prior beliefs about the world need to somehow be factored into this parameter, which is why this model is important. And then if everything is correct up to this point, you've kind of managed to find this prior, you've managed to find a model that can accurately sort of capture the true state of the world, then all you're left with is computation. And then you can worry about MCMC, variational inference, all these things, and you get your posterior and you're happy, right? And the device by which all these things are combined is obviously Bayes. So this is the machine that we really use in Bayesian inference. But you kind of make 3 crucial assumptions along the way that can sometimes hurt you. And the first of these is that the model that you pose, your conceptualization of the state of the world is correct in the sense that there exists a parameter in the space, in the parameter space, which recovers the true state of the world, at least approximately well. The second one is that your prior belief actually captures the correct and full prior knowledge you have about the true state of the world, which can be problematic. And the third one is that you can actually compute this thing. Because it's no good writing down a Bayes posterior if you don't actually know how to have access to it. We don't really want to work with Bayes posteriors on papers, right? We actually want to have the Bayes posterior to do stuff with. It comes from decision theory. We ultimately want to take decisions based on the posterior. So these are kind of the three challenges that you often face when you work with Bayesian posteriors in practice. So in other words, this really nice chain of logic that we have here has like three challenges at each of these steps. The modeling can be challenging and you might end up with misspecification. The second step, specifying a prior, might be difficult because you're kind of forced to express your beliefs in a probability distribution, which has its own difficulty. And there's like an entire field of study that I'm sure some of you will be familiar with. It's called prior elicitation, right? So there's people arguing about how you should do this in the first place. And then the third step that all of you will be much more knowledgeable about than me is the computation, right? You actually need to be able to translate this into something you can work with. And if you kind of violate these assumptions and you do have these challenges, there are problems arising from this. You have uncalibrated uncertainty, so it kind of becomes questionable whether it's actually that useful to compute the Bayes posterior in the first place, because your uncertainty might not mean what you want it to mean. And also you need to run your Markov chain for 3 years. So these are kind of the problems that you might end up facing. Okay. But let's pause for a second, because in spite of all these challenges, and I mean, I come from machine learning where people ignore this all the time. They do Bayesian inference anyways in some approximate form. And surprisingly, miraculously, it still kind of sort of works. So this is the mystery here. Like, why does this actually continue to make sense when it shouldn't, right? So we've violated Bayes' rule as badly as we can. We've taken the baton, we've hit it on the face, but somehow Bayes' rule keeps on giving. And one possible explanation, and the explanation I will advocate for until lunch, is that Bayesian inference corresponds to an optimization problem. And oftentimes this optimization problem can be well motivated, even if you're not in this very clean setting that we've set out at the start. Okay. And in particular, we've probably seen variations of this problem before over the last couple of days, right? So this is sometimes called the elbow. Here I've decomposed it slightly differently. The Bayesian posterior solves a really nicely defined unconstrained optimization problem with a regularization term. So your regularization term is the Knoblauch divergence of Q from pi. I learned something, which, as we all know, will be minimized if the two are the same. So here you're trying to drag your solution to the prior, and that is sort of in competition with your data term, which is just the negative log likelihood of your data. Here, for simplicity, I've assumed a decomposable model, but you can ignore the sum, right? You can just plug in the negative log likelihood of likelihood you put in here. And this, if you solve it, gives you the data. So you can see we're basically trying to trade off two terms. One pulls us to a point estimate at the empirical risk minimizer, or the MLE, as we like to call it in statistics, and the other one pulls us to the prior. And so rather than thinking of Bayesian inference as an updating procedure, this gives us a second perspective, looking at it as a variational problem, right? So we have not made an assumption about approximation anywhere here. This is always true. And actually, I think I have a proof on the next slide on why this is true. And it's a very simple proof. All you do is rewrite this inner term as a Knoblauch divergence. So notice that everything here is in logs. So we have some logs and we add them to more logs. Great, we can swallow them up into this fraction. Now, if you look at this fraction, I've added the z here. The z is the normalization constant of the density in theta of this lower term, okay? And so that's why I can add it here, because it doesn't actually depend on the thing we're optimizing over, so we're happy. But then notice that actually this is just the Knoblauch divergence between these two terms, and we're minimizing over the first. The Knoblauch divergence isn't a distance, but it's minimized if and only if both arguments are the same. So therefore, the unique minimizer here is exactly this, which we know to be the Bayes posterior. So it's a very simple and elegant chain of arguments that leads you to this. Okay. Now, once you kind of have this, one thing you can think about is that you now have a puzzle piece with 3 different components, each of which has like a very clear role in this optimization problem. And we can start playing with them. And over the last couple of days, we've played a lot with this bit, the space over which we optimize. And that's called variational inference. It's like a well-studied problem. You can also play with the other components. So when you play with the second component, you end up doing something that some people call pseudo-Bayes or quasi-Bayes or generalized Bayes. It has many names. You can also call them Gibbs distributions, right? Also Pack-Bayes. So there's loads of names, but you can play around with this loss function. And one particularly interesting application we're doing this in light of the sort of assumptions that I outlined about Bayesian inference earlier, is actually when you have misspecification, right? So we know that the log likelihood is actually a terrible loss function to be minimizing if your model isn't a good description of the data generating process. This kind of well-known and frequentist literature for forever. And so you can play around with this loss function and plug in some perhaps robust alternatives to rectify this issue. And then the third component of the problem is the regularization term. And so in the last talk, we saw that people have considered playing around with regularizer. I will note, in the last talk, this regularizer wasn't actually between the prior and the thing you're optimizing over, but it's between the posterior and the approximate posterior. So it's slightly different, but the logic inherent here is similar. Okay, and yeah, we proposed this in 2019, and I got rejected from a couple of places, but it's finally been accepted at Generalisations this year, so hey. Okay, and so once you do this, you end up with this shorthand form of the problem, right? So you have three arguments. You have a generic loss term now, which need not be the negative log likelihood. You have a generic regularizer, which for simplicity will take this to be a divergence. So it's zero only if and only if both arguments are the same, and it's generally non-negative. And we have some space pi, which may not even be a variational family, but it could be. But it could also be the space of all probability measures or something else funny that you've dreamt up. And it gives rise to this belief distribution over the space theta of parameters that indexes your loss function. So I'll sometimes be lazy and I'll just write this. So this exists. The other remark here is that in spite of me having phrased all of this for parametric families, the same logic you can actually apply even in non-parametric spaces. And so this is something that was done by Dino and one of his PhD students fairly recently. I think it's they presented this year at NeurIPS actually. So this is fairly recent, but the same arguments, slightly more complicated because densities don't necessarily exist on infinite dimensional spaces, but you can sort of make the same arguments, which is kind of nice. Okay, so right, great, we have this generalization, but why should we bother? I've already probably motivated why I think we should bother, but you can also sort of take this and certain special cases recover lots of things people have studied before. I've alluded to this, right? So we have standard Bayesian inference, of course. We have what we've discussed the last couple of days. We have a variational inference. We have PAC Bayesian posteriors or Gibbs posteriors, which are the case where you look at specific loss functions here for their generalization properties, basically, and you study them in the frequentist sense. But when you actually look at the minimizing argument in the PAC Bayesian inequality, it happens to be exactly this type of form. And there's a couple of other generalizations. One of the ones we studied a lot originally was what we call generalized variational inference, and I'll speak about that a bit later. And it's basically just a case where you fix a variational family Q. So we do what we've done all week, but then you play with these two terms. Note that there's no longer an approximation to the base posterior, right? You're changing the problem. So you probably do something that's quite similar, because normally you don't depart infinitely from the objective that you pose when you pose the variational objective, but you're not trying to approximate the base posterior anymore. So the name is perhaps slightly confusing in the context of the last week.
General question, does this also include the case when you have an improper prior?
Good question. Generally, no, because some divergences might just be infinity in that case. So the KL is sort of special in that sense that it still makes sense. But if you play around with divergence, you might run into trouble. Okay. So in general, this is restricted to proper measures. Okay, so I've mentioned PAC bounds. So a PAC bound, if you've not seen them before, what they basically are a probably approximately correct bound. Sorry. So it's basically a probabilistic generalization guarantee where you're trying to bound some expected loss. So let's assume we have some population expectation over the loss that we're targeting, and we want to see how badly we do in the sample that we have. What we're basically doing is we're posing a uniform bound over all distributions Q, and we can usually show that under some assumptions, in this case, boundedness of the loss, we get these kind of inequalities, and they hold with high probability. And you can see that if you actually want the best of all these bounds over Q, what you would do is you would minimize the right-hand side, which depends on your data, over Q. So this actually has the exact form that we've studied on the previous slide, right? Where your discrepancy now takes some form that is a bit weird. But the point here is this is still a proper divergence. And this kind of objective arises in a completely different literature. And it's kind of a motivation for very different literatures arriving at this generalized form for very different reasons. So in this case, it's the desire to get out of sample guarantees for something that you minimize in sample. And I will note that, so this depends on some function of the KL, but there are other packed Bayesian inequalities that will depend on other divergences. Okay, then maybe you're also familiar with this literature on cold posteriors or weighted posteriors or power posteriors. They have different names in different literatures. What they basically are is these objects here, where you've now raised your likelihood to a power, which incidentally means you're actually not following Bayes' rule anymore. So the moment you see a power posterior, you've already departed from Bayes' rule anyways. And what you're basically saying is you want to weight the original log likelihood with some W. There's another example. It's a very tame example, right? It's a very tame departure from the normal Bayesian procedure, but it is one that is quite popular. There's actually loads of them. I don't have time to go for all of them. There's like a table, which is in itself incomplete, but people have considered various ways of sort of relaxing this slightly with idiosyncratic motivations in each case for why this is a reasonable idea in this specific context. So really the point of this slide is to say, people are doing this anyways, so perhaps we can sort of create a coherent framework conceptually for why this might be an interesting problem to study more generally. And one thing I want to note before we move on to the theory bit is the relationship between this and sort of the standard variation inference framework that we've discussed this week so far, and where they two coincide. So they obviously coincide if we use the Coburg-Lapid divergence as a regularizer. And in this case, you know this picture probably, which just means you use the KL projection into the set of parameterized distributions that define your potential posteriors, right? And you're trying to minimize the KL divergence into this set. I call this the discrepancy variational inference set of mind, because there are alternative distributions people have tried to minimize. So there's some literature on minimizing Renyi alpha divergences, certain other F divergences. There's a framework called operator VI. What they all have in common is that they look at the problem like this. You're trying to find some sort of pseudo distance, and you're trying to project into this space. So you're trying to minimize the distance between your candidate posterior and the true posterior. But the view that you can also actually adapt, and which comes from this proof I showed you earlier, is that actually standard variational inference is just the constrained equivalent of the full optimization problem. So if you optimize the objective that underlies the base posterior over the full space of probability measures, you arrive at base posterior. If you don't change the objective, and the only thing you change is the space over which you optimize it, you get the variational inference posterior. So if what you really care about is this objective, then in some sense, you can never do better than the variational inference posterior. Once you fix the variational family that you're willing to pick your distributions out of, and you say, this is actually the objective I want to minimize, you can't do better by definition, because it's basically the constrained minimum. That's what the variational inference posterior is. And that's kind of funny, because basically it means that in this very specific optimization-centric sense, the variational inference posterior is the best you can do. And once you fix the variational family, you can't do better. And lots of machine learning people at this point will jump out of their seats and shout at you and object, because there's a rich literature on alternative ways of constructing these approximate posteriors, even if they lie within the same family. And there's a good reason for this. And they can often, capture certain characteristics better than the standard variational inference posterior. So we talked about expectation propagation earlier in the week. That would be an example, right, where you look at the reverse KL. And this is very true, but there's still a way in which I can kind of get a sense for what I mean with this suboptimality. And this picture here, I really like to sort of illustrate this. And in a sense, it is that standard variational inference still respects the same loss function as the base posterior. And that loss function, remember, is the negative log likelihood. So what I've plotted here is a mixture model. So it's a two-component mixture model, which means there are two places in the parameter space that are equally good, right? Because we have two components, we can just swap the labels and they're equally good. And as you can see from the black line, which is the full base posterior, these are here and here. So actually, if you really care about the loss function, you don't care about either of these 2 points, they're equally good. So what happens if we fit variational inference? It basically picks up on the mode that's slightly higher under the prior, and all the mass concentrates on this. which in some sense isn't great for uncertainty quantification. But if you care about the loss function underlying this problem, it's not that bad because you're getting one of two equally good solutions. If you use a generalized variational method where you basically use Rennie's alpha divergence for the divergence, so basically what it leads to is you get slightly more conservative uncertainty quantification, you get this blue line. So you're still focused on one mode. But what happens if you do one of these projection or these discrepancy variational methods is, and this is one that's what's it called? Covering? I forget. Mask covering, that's the one. When you do one that's mask covering, what you basically see, and this is the green line here, is your mode of your posterior relief now is in the locally worst position. So you're actually having a map estimate that does not respect the loss function in some sense. So very much depends what you want to use your posterior for, but if you care about the underlying loss function, this is what you pay for, essentially. Okay, just so this is a cautionary tale. Think about what you want your approximation to do before you compute the approximation. Okay, I feel like I've been monologuing. Are there any questions at this point that I should take?
Could you come up with other loss functions that you would still minimize with Bayes, but like would get you these other VIs, right? Because when you showed that proof, you just needed that the prior was like the minimum, like minimize that divergence or something. Is that right? Like if you replace the KL divergence here with a different divergence,
Yeah.
it's still minimized at the base posterior, right?
So what's the question? If you replace the KL?
I don't know, like, does that need, okay, that does need to be the KL divergence for this.
You basically need the KL for this because the log is additive. That's really the KL in a nutshell. It explains why it's like in 90% of the cases, why do you use the KL rather than something else? The answer is the log is additive. And that's basically what you use here. So if you replace the KL with something else that was an expectation of the log, you wouldn't sort of be able to absorb it and rewrite it in this way.
But you could change at the same time the red thing and or the orange thing and the green thing and
You could, but it's additive, right? You still need to absorb them. You still need additivity between those two. And that's, you're not going to be able to absorb that with the same divergence at least. So it's possible that you might get a different divergence down here, but I haven't seen that. Yeah, okay. I haven't seen that. I will actually show a result later, which is really cool, where Pierre Alquier, Badra's former supervisor, he has shown how you can solve this problem under some restrictions for general F divergences. And it relates to Penfield conjugacy of the function upon which the F divergence is built. And you find some truly strange animals if you do this. Other questions at this point? Okay, so I will probably rush over the theory a bit, because that's probably not the most interesting thing, because these problems, because of how generally we frame them, are really difficult to analyze. So you can usually make only rather weak statements. Sorry. Am I allowed to talk? Yes. All right. Okay, so I think I'll skip this. So you can basically motivate why this problem should look the way it looks when you make some axiomatic assumptions, but these are basically the assumptions we've already imposed anyway, so I'm not going to go over them. By the way, if you want to look up anything on the slides I'm not covering, or you just want to have these slides, if you go to tinyurl/this number here, you can find them there. Okay, so one of the questions obviously you need to ask is, do these posteriors exist? Are they unique? And basically what you use here is convex analysis. It's on a Banach space generally, but the answer is generally yes. If your divergence is convex and continuous, or I should say lower semi-continuous, because that's actually enough. And you basically need no regularity under this, they exist as a minimizer. And then the question becomes, is it unique as well? And you can I'm going to skip this. You can basically show it if your divergence is strictly convex, right? So
can I ask what n is here?
Sorry,
what n is?
N is the number of observations.
Okay.
Yeah. Because that's kind of, we need to later analyze what happens with these posteriors as n goes to infinity, right? So I've been indexing them with n here. Okay, so basically, under very mild assumptions on your regularizer, these things exist and will be unique, and you probably want your regularizer to be convex anyways. So there's nothing to worry about on that front. Okay, so this is some more theory that relates to what I just said about using F divergences. So essentially, when you plug in an arbitrary F divergence as the regularizer, and you base it on a function F, for which you have the Penfield conjugate, and then you take the derivative of that Penfield conjugate, what you can basically show is that the optimum posterior as a density looks like this, where this lambda star, I'll explain, this lambda star is basically your Z now. So the lambda star is the normalizer. So you have you plug your loss function in here. The eta, by the way, is just the weight you put on the loss. So you can it's like the weight in the power posterior. Okay, so we put a weight on the loss, and then we have a density here. If we integrate this, it should integrate to 1, obviously, and that's basically how you determine lambda star. This might be quite vague, quite abstract. So obviously, this example, the Gibbs posterior, it works for this case, obviously, but you don't really need this theorem to explain this case. So let's look at the chi-square divergence. The chi-square divergence leads to this Penfield conjugate. And so what this basically leaves you with is a posterior that looks like this. The plus here means you take the maximum between what's inside this function and 0. And so you end up with a fairly strange creature. This also only exists under fairly restrictive conditions. So I tried to actually derive this a couple of days ago. And basically what you need is that this loss term is sort of bounded between something like 0 and 2, because otherwise it might not exist. But it's quite interesting. You do actually get these kind of results. Okay, what else can we do? We can kind of look at this Penfield conjugate a bit more, but in a different space. And we can look at the dual problem that is posed by our optimization problem, right? So we have an infimum over the space of measures. An immediate question a person that works in optimization will ask you is like, well, what's the dual look like? Can we do something cool with the dual? So we tried to do something cool with the dual. I'm not sure it worked, but we do have some results that we published this year at the conference on international learning theory. No, sorry, International Conference on Algorithmic Learning Theory. That's it, ALT. And basically, what you find is a strong duality that's slightly weird, but also kind of cool. And it looks like this. So let me decompose this slightly. So you have the expectation from before. You have a space FB, which is the space of bounded measurable functions on the parameter space. And you're now looking at a sup over an inf. So immediately you can see where the adversarial robustness comes from. We're trying to take an infimum over something, but an adversary is trying to make our loss as big as possible. So the adversary acts on this space FB, the bounded measurable functions on theta. And what the H that the adversary chooses basically amounts to is a perturbation function. So we're trying to minimize this loss. The adversary is trying to push up this loss with some function H, but also the adversary can't do this indefinitely. So otherwise he could always make our loss infinitely large. And so the adversary gets penalized for making the perturbation H larger with a strange cost function. And this cost function is determined by the regularizer we've chosen and the prior. And what this basically looks like, if you zoom in a bit on this term, is that the prior becomes a weighting function. And the more prior mass you have in a region, the more expensive it becomes for the regularizer to push the H function into higher regions in that space of the parameter. Okay. So all of this looks fairly abstract, but it actually has a very nice interpretation. And the other thing you can show, so there's a second duality result, that actually, when you compute this posterior, the posterior is part of the infimum of this expectation. So the H star here is actually the function that the adversary ends up choosing. Okay, so this is the function that is best for the adversary that makes our loss the largest. Or remember, this is our loss, but then we get less loss from what the adversary actually picks. And we actually end up picking a posterior which makes the original loss we were targeting plus the adversarial, the adversary's perturbation the smallest. So it's kind of interesting. The slight problem with it is that the set, this arginf set, is not unique. So there's multiple distributions in that set. So this is not a unique element. But nonetheless, the posterior you find will be one that is in this set, which is kind of interesting. Is it methodologically useful? I don't know. Sorry.
Go back to the, we agree that in the definition of the gate, it's like a P in the divergence.
Sorry?
In the definition of the conjugate.
Yeah.
It's not the P in the divergence.
P and the divergence.
Oh, it should be a P in the divergence. Yeah, you're absolutely right. Yeah, so yeah, okay. So this here shouldn't be Q, it should be P. Yeah, sorry. Well spotted. Do you have fun doing this? All right. Yes. Okay. And so yeah, basically the interpretation that I've written on the slide is just the one that I've just explained to you. You have an adversary that is trying to push your losses into unfavorable places, right? But the adversary pays, and what the adversary pays is what you determine what the adversary pays by specifying your prior and your divergence. Okay, so the second question you might ask is whether the sequence of distributions, so the Qn star as a function of n, as n goes to infinity, is actually consistent, provided that you've sampled your data from the same population. And this is really, really painful to actually do. I wrote a paper on this a while back, and it's not fun because you don't have a closed form solution. You only have an implicit solution as a solution to an optimization problem. So you need to rely on something called gamma convergence, or sometimes called epi-convergence. And the problem with this stuff is that you basically don't get convergence rates. So you do a lot of labor, and then what you get is you get that the thing is consistent, but you have no idea at which rate. So I'm going to skip all the technical details. Basically, through a lot of labor of love, you can show that this thing is consistent as n goes to infinity. If you want to read about this, I have a paper on this. If you want to torture yourself, I don't recommend it. I'm quite happy that's passed me. But okay, so this is some theory. Obviously, we're still working on improving the theory. There isn't a lot out there. It's very patchy. And so at least in the most general sense. So for certain subcases, we have more theory available. So the moment you choose the KL as a regularizer and you have differentiable loss functions, the world is your oyster. There's loads of things we can prove in that case. Okay, but so in the last part, we'll go through some sort of applications of this logic to sort of hopefully demonstrate that it's useful going through all this pain of proving consistency and so forth, because you can actually do some interesting things with this. Okay, so one of the first things that I think about is prior robustness. So what this means is you might have specified a prior that is perhaps not a complete reflection of the knowledge you have about the world. And if your prior is in radical disagreement with your data, you might prefer to listen to the data rather than insist that your prior belief was correct. This doesn't really happen in traditional experimental science, but it does happen in machine learning, where your priors are often, just default choices of distributions. You just choose a standard normal. If you know how Bayesian neural networks work, people just use a fully factorized standard Gaussian over the entire neural network. There's no reason to believe that's a good prior, but they do it anyways. So in this sense, your prior is very certainly misspecified. And what would we like this prior to behave like? Basically, if the prior is the only problem, we're kind of happy with the loss function. We want the prior to behave like the KL up to a point. So if you think of something like a Huber loss, you basically want the divergence to behave a bit like a Huber loss. You initially get a quadratic loss, and then you taper out as the disagreement becomes more extreme. And actually, it so happens that Rennie's alpha divergence, which we heard about earlier, does behave this way. We have some limited results on why this is the case, but I think they need some refinement. And this is an illustration of what this divergence actually looks like in practice if you do this. So we're just plugging in the Rennie alpha divergence here in the bottom for two choices of alpha. And in the top row, what we do is we use a weighted version of the KL. And essentially, what you find is as you have a more and more misspecified prior, so from left to right, the prior is increasingly more misspecified. At the left, it's centered at -5. And at the very right, it's centered at -50, which is completely off where the data actually occurred. And so what you basically see, very unsurprisingly, if you do variational inference, you're still trying to approximate the base posterior, right? So what happens is you just get flatter and flatter posteriors, and this effect is exacerbated if, and I should have mentioned, it's 1 over W times the KL. As you increase the weight on the KL, so 1 over 0.3 here, this becomes flatter and flatter. And what's kind of interesting about Rennie's alpha divergence is that it sort of doesn't care about the prior beyond a certain point. So you do see a shift from a reasonable prior to a misspecified prior, but you barely see any shift from a misspecified to an extremely misspecified prior. So you're just becoming unsensitive to priors past a certain point. So this kind of Hubert loss type behavior is one that we observe here, which is nice. And yeah, there's an application that we ran this on Bayesian neural networks where you can basically see that it works the way we expect it to. The second thing that you might worry about is likelihood misspecification. So if you remember the diagram from earlier, right, we had the likelihood misspecification, the prior misspecification, and the computational problem. I'm probably not going to speak much about the computation problem because we've spoken about it a lot the past couple of days. But let's assume you have some likelihood misspecification problem. In particular, let's look at the sort of canonical misspecification problem, which is the epsilon contamination problem, which basically means you have some fraction of the data here in gray, which is well described by the statistical model you pose, and you have some contamination component, some component that's like not in agreement with any parameterization of the model, and that's the black bits here. And often the most natural way to think about a contamination model is in terms of outliers. But note that that's not exclusive. You can always write any true data generating process as a sum of 1 minus epsilon, a parameterization of the model you pose, plus some contamination. It might be that your epsilon is extremely large, and if the support of your model is disjoint with that of your of the true data generating process, then the epsilon is 1, for example. But you can always do this. So this is actually a fairly generic framework of phrasing misspecification. And what we'd like is a kind of loss function that takes your model, but doesn't suffer the problems of the negative log likelihood. And to sort of illustrate what the negative log likelihood does in this case, you can see this orange line is a variational posterior fitted with a negative log likelihood, and it essentially tries to over smooth to this contamination. Now, this is like a well-known result in traditional robust statistics, and it's because the log likelihood does not have bounded influence. This here on the right is the so-called influence function. In this case, it's an influence function on the posterior itself, so it's slightly more difficult to define. But if you know what an influence function is in a frequentist setting or the point estimator setting, you have a rough understanding of what it means here. What it means is, how far can I move the estimator? And in this case, the estimator is the posterior, right? So the posterior is just a measure valued estimator, effectively, because it's a function of the data. How much can I move my measure valued estimator if I move a single point away from where it occurred originally? And if you have unbounded influence, what it means is you can move your estimator infinitely far. And this is the case for a posterior constructed on a negative log likelihood, and it's the case for the maximum likelihood estimator. So you want something that doesn't have this property, that at some point, as you move the point away towards infinity, says, hang on, I stopped taking this point seriously now. And this is what you get with bounded influence functions, which taper off. So these blue curves here are bounded influence functions corresponding to the so-called beta divergence loss. And the beta divergence loss is still referential to a probabilistic model. And in this case, the same probabilistic model, but at some point just stops taking your data into account. Okay. This is sort of the formal definition of this. If you want to look that up, I think I'll skip this. But this is just the formalization of the idea I've just described, right? So you need some kind of derivative or derivative-like object for the posterior itself. As your contamination epsilon increases, and basically the way you do this in practice is you take the derivative as at epsilon equals to 0, and you want that thing to be bounded. And that's very similar to how you would define things in the traditional frequentist sense, and that basically you can extend this analysis to the Bayesian setting. Okay, so why do we care about the log? Again, kind of obvious, because the log pops up in the original objective we analyzed. And it's actually useful to rewrite this slightly and see that actually the log has a very intimate relationship to the Kullback-Leibler divergence between the true model and the parameterized model. And why is this useful? It's useful because we might hope to construct other loss functions in this way. So if we know the log function is actually derived from the KL, and we know the KL isn't robust, maybe we can use a robust divergence, plonk that in here, and derive a loss function for a probabilistic model from it. And this is basically the solution when you use the beta divergence as well. And so here's a project I worked on a while ago now, where we looked at online change point detection problems, where basically one of the problems you have is that if you get an outlier, your online change point detection algorithm will think a new segment of the data has occurred, even though it's like a blip. And here the red lines are the change points you declare when you have a standard vanilla algorithm which uses the standard Bayesian posterior, which is based on negative log likelihood, right? So all these outliers, and by the way, these outliers occur in 5 dimensions, so you don't even see them with your eyes. At least I don't see them with my eyes, right? The outlier is here, but we wouldn't be able to actually visually see them. There are 2 true change points, by the way, around 400 and around 200, but we declare loads and loads of false change points with the standard algorithm. And what you can basically do is replace the negative log likelihood with a loss function that has bounded influence. In this case, it's the beta divergence, and then you recover the correct segmentation. So this is actually what the algorithm delivers back at you. So that was quite nice. I'm going to skip this visualization. We did something similar with a different divergence in the context of deep Gaussian process regression. I have no sort of love for deep Gaussian process regression, but it was an illustrative example where your models are, in some sense, always going to be misspecified, because deep Gaussian processes on a computation level, at least at this point, it might have changed since. This is from 2018, I think. But at this point, they were really only working well if your likelihood model was a Gaussian likelihood model. So you had a lot of flexibility with the functional prior, but at the end, you needed to pump it through a Gaussian likelihood model. So what we did here is say, well, in all likelihood, most of the data these people look at might not be Gaussian. So we used a gamma divergence induced loss function. And basically, you could show that the test losses you got were consistently lower. So sometimes for a single layer, for a single hidden layer in the deep Gaussian process, we were doing better than a three hidden layer deep Gaussian process with standard variational inference. So the story here is it's actually a really simple change, even in the software you're using, and you're getting a quite phenomenal payoff, which was nice to see. Okay, so we've seen sort of improving misspecification, we've seen improving prior misspecification. The last bit, computation, we've spoken a lot about variational methods. So I'm not going to speak about that. I've worked a bit on that, but there's actually another way you can use these posteriors to kind of simplify your computation. And that is by choosing the loss in a way that's kind of smart for your problem. So that's something we've worked on in the past. And so I'll go over 2 examples of how you can do this for simulation-based inference and for intractable likelihood problems. Okay, so simulation-based problems, in case you're unfamiliar with them, basically what you have is you have a likelihood function that's only implicitly defined through some kind of computer simulator. So these models are very popular in climate modeling, in chemistry. I've seen them. Are often 10,000 lines of code, and it takes forever to run them. And the parameter theta in this case is like directly implemented in your code, and it generates some data. And you're hoping to find a version of the code that reflects the data you observe in the lab quite well. But you don't have a likelihood function. The likelihood function is only implicit in the simulator, right? So that's a problem for us. So one of the standard solutions to this problem is called ABC, approximate Bayesian computation, where basically what you do is you sample from your prior, then you run the simulator for that sample of the prior, you generate some fake data out of the simulator, and then you check whether the fake data that you generated is sufficiently close to the data you've actually observed in the lab. And if it is, you keep that sample that you sampled from the prior, and otherwise you discard it. Needless to say, that's quite wasteful. So a lot of your prior samples, you will have to run the simulator, which again takes hours perhaps, and then you have to throw away that sample. So it's no good, basically. So for example, in one application I worked on, you ran this 10 to the 7 times, and you could only keep 200 samples. And this is after you've been extremely generous with your prior. So your prior is already defined on a compact domain, right? You're already trying to make this as simple as possible for the algorithm. But it's unfortunately often quite computationally unfeasible. And one of the solutions actually is to compute a posterior that is based on a sample-based loss, because one of the problems here is that you're still relying on the likelihood, and it's the likelihood that isn't computable. So perhaps you can compute something that is actually easy to compute from samples from the simulator. And one example of this is the maximum mean discrepancy. So Butter, I think, was the first to propose this in the context of Bayesian methods in a paper in 2019. And then there's some follow-up work from myself and some colleagues, and Lorenzo Pacchiario, who's I think at Oxford, so some of you might know him as well. And basically the idea is, rather than bothering with the likelihood in this case, we can target directly this loss function in this formulation, where the loss function now relies on expectations only, right? So one expectation is over the empirical measure, so the true data that we've observed. The other expectation is over the parameterized model or our simulator. So what we just do is we sample a couple of times from our simulator, and we can approximate this expectation, and we can approximate this expectation, and we therefore get a loss function. So none of our samples from the simulator actually go to waste in this scenario. And so each of the samples, even if it only leads to a small contribution to your final posterior, does lead to a contribution. So it's more sample efficient usually. Yeah, so you need fewer runs. And as an added benefit, actually, if you choose the right type of kernel, and when I say the right type of kernel, it really only needs to be bounded. So any standard kernel you choose, like a Gaussian, a Matern kernel, this thing will be provably robust. So as an added benefit, not only do you speed up computation, but actually you make the procedure more robust. You also get the right kind of convergence results, and you get a Bernstein-Hormesis result with mild conditions. And just to show you one of the examples that we have in our paper, you actually see a huge difference with something like Wasserstein ABC, for example, where Wasserstein ABC will sort of concentrate quite quickly. And in this case, also on the wrong spaces, because the model is misspecified. And in contrast, we sort of get more adequate uncertainty quantification on top of this being computationally much more feasible and robust. Okay, so the other example, I'm also mindful of time, so I won't stretch it too far. I think this is the last example I'm going to go over. And the second example, so this is something we did fairly recently. So this is going to be published at JRSSB this year. This is for the case of intractable likelihoods. So if you have an intractable likelihood, the normalizer of your likelihood is unknown. So we have access to this p tilde here, but this p tilde doesn't integrate to 1. And so that's a bit of a problem. And this generally leads to doubly intractable posteriors. And what that means is you don't know the normalizer of your posterior, but you also don't know the normalizer of your likelihood. So you're a bit screwed. Can we simplify this? And the answer is basically normally, yes, by approximating this Z constant. But that's complicated and it might not apply to all models in the same way. You need to do a lot of careful thinking how you're going to design your algorithms. So it's a bit difficult. But one thing that we were thinking of that actually simplifies this problem quite drastically is if you choose a loss function that takes into account this model, but doesn't depend on Z theta. And there's actually a family of sort of loss functions that does this for you. And they're based on Stein's method. And one of them you can construct based on reproducing kernel Hilbert spaces. And that's basically what we stuck with. So the details aren't so important, but basically when you choose this loss function, you get a V statistic. And that V statistic depends on some operators that are constructed from Stein's method. And the operator itself depends on the parametric model, but only through the gradient with respect to X of the log of your likelihood model. So that means the Z theta term goes away because first you take the log, so the multiplicative thing becomes additive, and then you take the gradient and the additive thing doesn't depend on X, so it's gone. And this is actually very neat because you have no doubly intractable posteriors anymore. So you've reduced the problem, it's singly intractable, and as a bonus, for exponential families, you do actually get a closed form posterior. So something that was previously doubly intractable, you get a closed form solution now if your prior is normal. Because for all exponential families, basically, what happens if you choose the, so if you want some details, this is the Langevin-Stein operator. If you choose the Langevin-Stein operator, this thing actually you can rewrite as a quadratic form. And that's nice. because the quadratic form is exactly what the Gaussian looks like. So if you multiply the exponential of the quadratic form with a prior, it's conjugate. So you get a closed form posterior. And that's actually surprisingly useful for a lot of settings. Again, as an added bonus, again, if we choose our kernel the right way, we can also show that the resulting posterior is once again robust. So you get that for free. And we get Bernstein von Mises results. And we can kind of show that you get the right coverage if you're careful. Okay, so one example here that we actually looked at was a protein signaling network where people are kind of interested in detecting which kind of proteins activate together. You can put some noise into this network. So here the epsilon, so it's epsilon 0.05, epsilon 0.002, epsilon 0.001, epsilon 0 tells you how much noise we injected into this problem. And basically, you can't actually do normal Bayesian analysis for this model at all. Like we didn't find any algorithm that would have worked. But what we did do is do two different versions of this KSD base procedure on the problem, and one where we chose the kernel to not be robust, and one where we chose it to be robust to kind of demonstrate the effect. And what you basically find is that this network looks very different if the loss function isn't robust, which is kind of unsurprising, right? So this is reinforcing why you want to care about misspecification. So you might draw completely sort of spurious conclusions from the activation networks, depending on the amount of noise in this network, versus the robust version, which fairly robustly sticks with the same associations. So whether these associations are meaningful is a different question, but at least they're stable, right? So at least it's not as brittle.
These are pictures of like map estimates or something like this?
Sorry?
These are pictures of like a map estimate of the network? Or?
Yes, yeah. Sorry, yeah, should have mentioned this, yeah. Okay, so actually I have one more example, but I promise that will be quick. Very recently, I mentioned earlier that this optimization problem has been transferred from the parametric setting to the non-parametric setting, right, to the infinite dimensional setting. The work that did this, they basically proposed this objective where your regularizer now is the Wasserstein distance. And the reason they choose the Wasserstein distance is quite interesting, because in the infinite dimensional case, actually using the KL divergence for a variational setting is quite complicated because you don't really have densities. So it becomes complicated to evaluate and you can't actually compute anything. So what they did instead is propose Wasserstein because if you use Gaussian measures, so these are random variables on function spaces. If you use Gaussian measures, the Gaussian process is an example of a Gaussian measure, but they're more general. If you use Gaussian measures for this, you actually even get this in closed form. So suddenly you have like a very elegant way of doing a form of uncertainty quantification in infinite dimensions for something that previously with the standard KL regularizer was quite unattainable. And so I'm bringing this up because in this case, we're actually doing it for computation again. So we don't sort of care about prior misspecification in this case. All we care about is actually we can compute the Wasserstein. So this is a setting where we couldn't even do the other thing. We couldn't even compute the KL between these two objects. And yeah, this is again due to the three people I mentioned earlier. So this is the same paper that's going to be presented in Europe this year. Okay, so this is also the point where I want to wrap up. Okay, so just to recap, Bayesian inference is a particular optimization problem, and it's one that needs you to make strong assumptions that you may not want to make. And I hope that I've convinced you that sometimes, and in particular in machine learning, you may want to venture outside the conventional optimization problem that we're focusing on a lot as a discipline and try some other stuff. And hopefully it can actually do something interesting for you. And if you're interested in kind of this direction, obviously I'm very happy to chat about this because it's kind of what I do. So we should have a chat over a drink later today. And yeah, I think that's where I'll finish. Here's some of the references. The slides, as I said, you can find at the tiny URL. And if I don't know whether I'll still have a Twitter, so I'm not going to advertise that. Okay, so are there any questions before we have lunch?
Can I ask if you've done any stuff that involves latent variables? Basically?
No, it's an excellent question. So no, I've not really focused on latent variables. So for example, also Camelia's talk earlier focused a lot on latent variables because that's quite important in variational methods. It complicates this style of analysis a bit. So I've steered clear of that. But it would be an interesting direction to sort of sprout into, because I think it raises interesting questions I hadn't really thought of in the past. Yeah.
It would be nice to work it out because you have the nice thing, the posterior of the joint and the posterior of the muscle system with one another.
Yeah.
So once you start twiddling the knobs, it becomes tricky. But it would be cool to work it out.
Do you want to do it?
Right.
Let's do it.
I mean, the filtering problem is not exactly the same, but somehow that's also, is the change point detection a filtering problem or is it a direct?
That's a good question. I think you can frame it as a filtering problem, yeah. It's the state space is a bit weird because you never revisit a state in this case. So you're always declaring, you never go back to a previously observed segment, but I think you can still frame it as an infinite state space where you, yeah.
Just one more thing. So with the usual objective, you have standard base. That's something you can use for model selection typically. Does the same hold here in a meaningful way?
So you can't really, yeah, this is an excellent question again. So you can't really do model selection with this stuff. And the reason is that you usually when you do model selection in the standard base case, right, you assign meaning to the value of the objective. But if you change the objective, you completely change the scaling of the minimum. So we're really looking at the argmin here. We wouldn't care about scaling it with an arbitrary W. So the general answer is no. There's one paper by Jack Jewson that's just got accepted into JRSSB. And what they do is they do a kind of model selection in this general setting where they do loss function selection, basically. And the way they do it is effectively with the same trick that we use for the KSD, where you're saying, well, the thing that differentiates a likelihood function from an arbitrary loss function is the normalization. So if we pump both of them through something like a score matching or KSD procedure, they lose this and they kind of operate on the same plane, and then they become comparable. But it's not sort of model selection in the traditional Bayesian sense. So yeah, you can't really do this with this stuff, which is unfortunate. Thanks.
I have another question, Mike. Could you briefly go back to in the slides to the point at the soup of the mean?
Oh, the adversarial robustness.
Yeah, exactly. Could you go over that a little, like one more time, please? The intuition line.
This one or the next one?
This one.
So what it is basically is you have this interior infimum. So this is what you're trying to minimize. So you're trying to minimize over the space of measures this loss function, in this case unregularized. Instead of the regularization, what you have is someone who kind of tries to throw you off. So imagine you want to.
I don't understand the function, like not the function, but like why we want that.
What do you mean?
Why do I want to be thrown off from the?
Oh, it's a form of robustness, right? So if you are robust effectively, what this tells you is that if you have a base posterior, and this is what the result on the next slide basically also tells you, this base posterior is in the argin. So if you know by how much I'm going to try to throw you off, you will actually compute a posterior that still manages to be in the arginf of the expected loss plus what the adversary chooses to throw at you. Mm-hmm. So you're robust against an unknown adversary trying to disturb you. You don't observe this adversary, it's completely fictional, like it doesn't exist, right? But it's like if nature tries to throw you a curveball, it still guarantees robustness against some forms of curveballs. And this is what this curveball looks like. Okay. Does that make sense?
Yeah. Thanks.
There are some stuff in.
Oh, no, that's fine. Yeah, it's fine.
Just about the tiny.
Yeah. It's fine.
Okay. Well, let's think. Yeah, I think so. Let's think.
Pudding.